Okay, my name is Zoya and today, along with my teammates Aqsa, Tariq, and Laiba Farooq, we will be discussing the topic of deadlock, how to detect and prevent it.
We're going to discuss everything in detail about deadlock. What is a deadlock? How does it happen? And then we'll take a real world scenario and we'll compare it with the operating system scenario. And then we'll discuss about four conditions that need to occur in a system for a deadlock to happen. And lastly, we'll discuss about how to manage and deal with this deadlock situation. And we'll see some strategies used for deadlock avoidance or deadlock prevention. First, we're going to start with what is a deadlock? Deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. Because in operating system there are many processes and programs running continuously and these processes require some resources to finish their execution. For that, the process first requests for a resource. If it is available, then the operating system grants the resource to the process. If it is not available, then the process has to wait. After that, the process uses that resource, and lastly, it releases that resource. So, if a problem arises during the waiting and releasing, then it means that there is a deadlock situation. Let's consider an example where two trains are coming towards each other on the same track and there is only one track. So none of the trains can move once they are in front of each other. So this clash will create a deadlock. So let's see a real world scenario of a deadlock that happens in our day to day life. This is a basic scenario of a road traffic deadlock situation. As you can see, these red set of cars are traveling in a certain direction and these are blocked over here by blue cars. Again, blue cars are blocked over here by pink cars and these pink cars are blocked by yellow cars and the yellow cars are again blocked by red cars. In this situation, no car can move ahead because all of them are blocked by some other cars, where every car is waiting for other car to move ahead. But they cannot move ahead because they are indirectly blocking each other itself. So this creates a deadlock. Now let's see what happens in an operating system deadlock scenario. In this diagram, in green circles we have process 1 and process 2, and in blue boxes we have resource 1 and resource 2. So resource 1 is assigned to process 1 and resource 2 is assigned to process 2. But process 1 now requires resource 2 to execute, but resource 2 is assigned to process 2, so process 1 cannot access it, while process 2 requires resource 1 to execute. So both of them are in a deadlock situation, waiting for each other to release these resources so they can access it. So this creates a deadlock situation and none of the two processes can be executed.
Move on, guys. Now let's discuss how we can detect deadlock in our programs or systems. We will discuss deadlock detection. Make sure to write notes. So, what is deadlock detection and how can we detect it? Detect deadlock with the help of some recovery techniques, including resource allocation graph. It has all the information about the resource allocated to each process and the request of that process, where vertices showcase the process of the resource and edges represent allocation of any request. About the necessary conditions for detecting a deadlock, there are four: mutual exclusion, hold and wait, non preemptive circular wait, mutual exclusion. Only one process should be using the resource. If another process requests the same resource, then it should be put on hold and delayed until and unless the resource is freed by the first used process. Hold and wait should be a process that is holding a resource and other of the resources are being used by other processes. When they have finished it, they can share it. Non preemptive resources can be preemptive. A process will release the resource only when it has completed its task. Resources are one, so first of all they will finish their work, then they can take it somewhere else. Circular wait: P1 needs P2's resource and so on, but until the parent process doesn't finish its work of that resource, it won't be given to P1 and so on.
We've discussed what is deadlock and its characteristics, but how do we handle deadlocks? There are two ways of handling deadlocks: prevention and avoidance. Prevention is eliminating any one condition needed for deadlock whereas avoidance is checking beforehand and not allowing actions that could cause deadlocks. Let's first discuss how we can prevent deadlock. To tackle this issue, we must first look at the four conditions that need to be fulfilled to have deadlocks happening in the first place. Let's look into what each condition needs so that we can prevent it from happening. Mentioned is mutual exclusion. So, to prevent this from happening, do we get to share all resources? Unfortunately, some resources cannot be shared with more than one processor at a time, like printers, for example. To handle this problem, we use a technique called spooling. When multiple processors request for the printer, the jobs are added to a queue into something known as a spooler directory. The printer works on the jobs in a first-come, first-served basis, and the processor stops waiting to send the request and performs other tasks. Although we can use spooling, it can only be used with resources that have associated memories, such as printers. The condition we can eliminate is the hold and wait. As previously discussed, hold and wait functions such that one resource is being held by the processor while it's also waiting for the next resource to load. There are two ways to eliminate this condition: to eliminate the wait and to eliminate the hold. To eliminate the wait means that the process requests all the resources in advance and executes once all of them have been loaded. The second way to handle this condition, eliminating the hold, means that the process has to release all the resources it is holding onto before it can make a new request. Although we can use two methods to eliminate the hold and wait, the violation of this condition can also show challenges, such as the process being unable to tell what resource it needs until the time of execution. This makes us unable to load all the resources at once. The third condition is non-preemption. To eliminate this condition by preemption, we look at a scenario where a processor has some resources and is waiting for another resource. To fetch the next resource, it will be required to first release all of the first three resources that the processor is currently using, and to request all of the resources simultaneously. This is just like how we would request for all of the resources when we eliminate the wait in hold and wait. The last of the four conditions is circular waiting, which is when multiple processes wait for resources in a circular order. To eliminate this, we assign a priority to each resource. This makes the process access only resources in an increasing order of priority and unable to backtrack. One of the challenges of this is that it is difficult to assign relative priorities to resources, as it could vary depending upon the process. For example, a media player won't give a printer high priority, but a document processor might. With all of these methods of prevention, what conclusion can we draw? We can apply any of these to prevent deadlocks depending upon the situation. However, the most feasible one of the four is circular waiting, as the other three cannot be eliminated practically. Thank you for listening. If you have any questions regarding this topic, now is the time to ask.